Hey everyone, this video is on the molar enthalpy change of reaction. By way of review, enthalpy change refers to the changing energy of a chemical system when it undergoes a chemical reaction. The internal energy of a chemical system refers to both its kinetic energy and its potential energy. For most chemical reactions, majority of the changing energy of a chemical system throughout a chemical reaction is due to the changes in the chemical potential energy of the reactants and products. And this is discussed in detail in the video on bond energies. Recall that when we break apart bonds in reactants, energy is absorbed, and when we form new bonds in the products, energy is instead released. The relative difference between the energy absorbed and released will contribute to the change in the chemical potential energy of the reaction, which makes up majority of the change in enthalpy of a chemical reaction. These two energy profile diagrams shows you the change in enthalpy of a reaction for both an exothermic reaction, whereby the product have lower enthalpy than the reactants, and an endothermic reaction, whereby the enthalpy of the product is higher than that of the reactants. So in both diagrams, the change or the difference in the enthalpy of the reactant and product is known as the enthalpy change. And this is what we'll focus on in this video. For exothermic reactions, the change in enthalpy is less than 0, and for endothermic reactions, the change in enthalpy is greater than 0. The molar enthalpy change of reaction is the energy absorbed or released during the reaction per mole of a particular substance. And this is usually measured in the unit of kilojoules or joules per mole, or mole to the power of -1. What this substance is depends on the chemical reaction that the molar enthalpy of change refers to. For example, in the context of combustion reactions of a hydrocarbon or any fuel which produces carbon dioxide and water, the molar enthalpy change refers to per mole of the fuel. So in this case, in the complete combustion of propane, C3H8, the molar enthalpy refers to the fact that this reaction produces 2043 kilojoules of energy for every mole of propane gas combusted. So this per mole is not referring to any other substance in the reaction. It is specifically referring to the quantity or the number of moles of the fuel that's burnt. In the dissolution of a compound such as sodium hydroxide, the molar enthalpy is also measured in kilojoules per mole. However, the per mole is not referring to the fuel anymore, it is referring to the number of moles of the compound that you're actually dissolving. So here, this is also an exothermic reaction, which will produce 30 kilojoules of energy for every mole of sodium hydroxide dissolved in water. In neutralization reactions between acid and base, specifically a strong acid and a strong base, the energy is derived from the formation of water molecules, specifically the covalent bond between the hydrogen ion and the hydroxide ion. So therefore, this exothermic reaction will release -57 kilojoules of energy for every mole of water that's being formed. So this per mole is dependent on the quantity or the number of moles of water molecules. So even though the molar enthalpy change of the reaction has the same units for every single reaction, the per mole depends on the type of chemical reaction that you're referring to and ultimately the substance in the reaction. And as such, the total energy that's either absorbed or released from the reaction is equal to the product of the molar enthalpy change times by the number of moles. The number of moles here in the combustion reaction refers to the number of moles of the fuel. The number of moles in dissolution of a compound refers to the number of moles of the compound that's being dissolved. And the number of moles in an acid-base neutralization refers to the number of moles of water molecule formed between the hydrogen ion and the hydroxide ion. The energy released or absorbed by the reaction changes the temperature of the substance, or otherwise known as the chemical environment in which the reaction is taking place. The relationship between the energy released or absorbed by the reaction and the change in temperature is governed by this formula, where Q is the energy released or absorbed is equal to m, which is the mass of the substance, times by C, the specific heat capacity, times by the change in temperature. It's important to understand and for me to highlight that the m in this formula is not the mass of the substance that we saw in the chemical equations previously. This is the mass of the substance that you're changing the temperature of. And most of the time, this will be either the mass of water or the mass of the solution in which the reaction is taking place. I'll explain this further in the examples that are to follow. And as we said, the energy that's absorbed or released by a chemical reaction ultimately depends on two factors: the molar enthalpy change of the chemical reaction, and also the quantity, specifically the number of moles of the substance that's been consumed or formed depending on which chemical reaction you're talking about. By way of review, for an endothermic reaction, the energy will be absorbed by the reaction from the surrounding. And this causes the temperature of the surrounding that you're measuring to decrease. An exothermic reaction will release energy to the surrounding, and when the surrounding absorbs this energy, the temperature will increase. Let's go through a few examples. 4 grams of solid ammonium nitrate is added to 200 milliliters of water at 25 degrees Celsius. The molar enthalpy of dissolution of this compound is roughly 25.7 kilojoules per mole. So this positive value indicates that this is an endothermic reaction. Calculate the final temperature of the solution. Now, we can write a chemical equation to represent the chemical process or reaction that's taking place. So we have solid ammonium nitrate. When it dissolves, it will form ammonium ion as well as nitrate ion, both of which are aqueous. And the molar enthalpy change of this reaction is positive 25.7 kilojoules per mole. Now remember, the per mole in a dissolution reaction refers to the number of moles of the actual compound is dissolving. So we need to first find the moles of ammonium nitrate that is dissolved. And we can take the mass of the compound divided by the molar mass of ammonium nitrates. So we have 2 nitrogens, 2 times by 14.01, plus 4 hydrogen atoms, and then 3 oxygen atoms. And this gives me a number of moles of 0.05 moles. So the energy that's actually absorbed by the reaction is equal to the molar enthalpy change times by the number of moles. So it's 25.7 kilojoules per mole times by 0.05 moles. And this gives a total energy absorbed of positive 1.28 kilojoules. And if we convert this into joules, it will be approximately 1,280 joules of energy absorbed. Now, the temperature is of the solution. The solution is not the same as the reaction. The reaction is absorbing the energy from the solution, which is part of the surrounding. So the reaction is absorbing 1,280 joules of energy, and this exact amount of energy will be taken away from the surrounding. So you could say that the surrounding, which includes the solution, has lost 1,280 joules of energy. When we're using Q equals to 𝑚𝑐𝛥𝑇 to calculate the change in temperature, the Q here should be minus 1,280 joules because this represents the energy that's taken away from the solution. And the M here is not the mass of the solid, but the mass of the total solution. Okay, so that will be primarily the mass of the water in 200 milliliters, and then additionally the mass of the solid that's being added. Since the density of water is 1 gram for every 1 mil, we can expect the mass of water to be 200 grams in 200 milliliters. So the total mass here would be 200 grams plus the 4 grams, so 204 grams, but we convert this into kilograms, which is 0.204 kilograms. And we'll times this by the specific capacity of the water, which is 4,180. And the change in temperature is what we're trying to calculate. So the change in temperature is approximately minus 1.51 degrees Celsius or kelvins. So the final temperature is equal to 25.0 degrees minus 1.51 degrees. And that gives me a final temperature of 23.5 degrees Celsius. Let's go through an example using combustion reactions. Butane gas was burnt to heat 100 milliliters of water, releasing 2.45 liters of carbon dioxide gas at 298 kelvins and 100 kilopascals. So this is room temperature and pressure. The molar enthalpy of combustion is minus 2,877 kilojoules per mole. So first of all, we need to write a chemical equation to represent this reaction. So the combustion of butane, assuming this is a complete combustion, will produce carbon dioxide and water. So to balance it, we can start the carbon first. We put 4 in from the carbon dioxide to balance the carbon atoms, and we can also insert 5 in front of the water to balance the number of hydrogens. This gives you a total of 8 plus 5, which is 13 oxygens on the right hand side. So to balance the oxygens, we can put 13 over 2 in front of the oxygen gas. So to put in the states, this is a gas, this is also a gas, CO2 is also a gas, and the water here will be a liquid at RTP. It's important to write a balanced chemical equation for this type of question because in order to find the energy that's released by the combustion, we need to find out the number of moles of butane gas combusted. This is because for combustion reactions, the molar enthalpy change, which is in kilojoules per mole, is per mole of the fuel that's combusted. The fuel for this question is butane gas. Before we can find the moles combusted for butane, we need to first calculate the mole of CO2 that's produced. Once we can find the moles of CO2 produced, we can then work backwards to find the moles of butane gas that's consumed in the reaction. We have the volume of the carbon dioxide gas, and we have the temperature and the pressure of the reaction. So we can take the volume of the gas divided by the molar volume at room temperature and pressure, which is 24.79 liters per mole. And this gives me the number of moles of 0.099 moles. So therefore, the moles of the butane gas is equal to 0.099 divided by 4, because it's a 1:4 ratio between the butane gas and the carbon dioxide. And this gives me an approximate answer of 0.0247 moles of butane gas combusted. So the energy that's released by the combustion will be equal to minus 2,877 kilojoules per mole times by 0.0247 moles of butane gas. This gives me an answer of minus 71.1 kilojoules of energy released, which is approximately minus 71,000 joules of energy. Now, to find the temperature change, we need to use Q equals to 𝑚𝑐𝛥𝑇 equation. This represents the energy change and the temperature change of the surrounding. We are using the butane gas combustion to heat 100 milliliters of water, and that's ultimately what we are measuring the temperature change of, which is the water. So if the combustion is releasing energy, the water is absorbing the energy. So while the Q in the left-hand side of my working out is minus 71,000, over here, if I assume there's no energy lost to the other surrounding, this will be positive 71,000 joules. And the mass is of the water that you're heating, which will be 100 grams, given that the density of water is 1 gram for every 1 milliliter. So the mass here will be 0.1 kilograms. And the specific heat capacity of water is 4,180, and the change in temperature is what we're trying to calculate. This gives a final answer of 170.1 degrees Celsius or kelvins. So the maximum temperature will be 25 degrees plus 170.1, and that gives you a final answer of 195.1 degrees Celsius. We can round this to 3 significant figures. Alright, let's go through an example on neutralization between acid and bases. 75 milliliters of a 0.5 mole per liter solution of hydrochloric acid is added to 45 milliliters of a 0.8 mole per liter solution of sodium hydroxide. The final mass of the solution is 130.2 grams, and we are given that the enthalpy change of neutralization reaction is minus 57.1 kilojoules per mole. So hydrochloric acid plus sodium hydroxide will give me a salt, which is sodium chloride, and water molecule. All of these are aqueous, and the water will be a liquid. Now, by way of review, for the molar enthalpy change of neutralization, the per mole refers to the mole of water that's being formed. So that should be my first step to calculate how many moles of water are actually formed from this neutralization reaction. Now, we're given the quantity of the reactants, the acid and base. So we need to first find the moles of each reactant and determine what is the limiting reagent. So the moles of hydrochloric acid is the concentration times by its volume in liters. This will be 0.0375 moles. The moles of sodium hydroxide can be calculated in the same way. Its concentration times by its volume in liters, and this gives 0.036 moles. Since the two reactants react in a 1-to-1 ratio, we can compare the quantity and the number of moles directly to determine which one's the limiting reagents. Sodium hydroxide having a smaller number of moles or smaller quantity therefore is the limiting reagent. This means the number of water molecules formed will be equal to 0.036 moles as well, as the ratio between the sodium hydroxide and the water molecule, which is the product, is 1:1. Now, we have found the number of moles of water. So the energy produced by this neutralization reaction is equal to the molar enthalpy change, minus 57.1 kilojoules per mole, times by 0.036 moles of water. This gives me minus 2.0556 kilojoules of energy released, and that's approximately minus 2066 joules of energy released. This energy released by the reaction will be absorbed by the solution in which the reaction is taking place. So the Q value in 𝑚𝑐𝛥𝑇, when there's no energy lost to the surrounding, will be positive 2066 joules. And the mass is the solution that you're measuring the temperature of, which is given as 130.2 grams. So we'll write this as 0.1302 kilograms, and then C here we can use the specific capacity of water, and the change in temperature is what we are trying to determine. And the answer here is 3.78 degrees Celsius / kelvins. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.